The wavelength of a wave is the distance from a point on the wave to the next equivalent point on the wave. Now, this is easiest to visualize with a wave diagram like this one, which looks like a simple transverse wave fixed in time. The dotted line here is our equilibrium line, and then we see how far the wave is displaced from this line at each point. These 2 points are examples of adjacent equivalent points. If we look between them, we have exactly one cycle of the wave with this down and then up pattern. But we'll look more at how we can show these points are equivalent soon. If we measure the distance between these 2 points, then that will tell us the wavelength. It's important to stress that this distance will be the same for any 2 equivalent points, not just these 2 in particular. It also won't change if we increase the amplitude of the wave. You'll usually see wavelength represented by this Greek letter lambda, and then we measure wavelength in normal units of distance, like meters. Now let's see how we determine if the 2 points on the wave are equivalent. Well, 2 points on the wave are equivalent if they are at the same point in their motion. Again, it's best to see what we mean here by looking at our diagram and why these 2 points we've chosen are equivalent. First, if we draw a line parallel to the equilibrium, we show that these 2 points are the same distance from the equilibrium line. Also, they're both above this line, so we can say that they have the same displacement. However, this alone isn't enough to say they're equivalent. Many students will make this mistake in their exams, so make sure you remember there's something else we need to check. Remember that although the wave is travelling in this direction, the matter is only travelling up and down as the wave pattern passes it. If we think about what's happening at our 2 points, as the pattern moves to the right, we see that the matter is about to move up as a peak passes them. So we can say that they are both moving up. This is why this point here with the same displacement isn't the adjacent equivalent point for this point on the left. If we imagine the wave pattern moving right again, we see that this point will be moving down back to the equilibrium line, so it's at a different point in its motion. This is really important, as it means we don't have a full cycle of the wave between these 2 points. In this case, we don't see a peak between them. It's important that you know these definitions, but now let's look at a trick which makes measuring wavelengths much simpler. The wavelength of a transverse wave can be found by finding the distance between 2 adjacent peaks or troughs. This time we'll look at an example of a wave rather than a diagram. A spring we wave up and down to create a transverse wave. It's a bit harder for us to pinpoint 2 equivalent points, so instead we can look at these 2 peaks, where the wave is at its highest point above the equilibrium line. We can deduce that these 2 points must be equivalent. They have the same displacement, and in both the spring is about to move back down. So if we measure the distance between them, we can find the wavelength. We can also do the same with these 2 troughs, where the wave is at its lowest point below the equilibrium. Again, both of these points have the same displacement, and the spring is about to move back up at them. So the distance between them is also the wavelength. This is the most common way of finding wavelength in an exam, though be careful as you might be asked to avoid using this method or recall the more formal definition of wavelength. Now, so far we've only talked about transverse waves, but what about longitudinal waves? Well, the wavelength of a longitudinal wave can be found by finding the distance between 2 adjacent compressions or rarefactions. This is an example of a longitudinal wave, where instead of moving the spring up and down, we push and pull it so the coils move back and forth. There will also be equivalent points with a full cycle of the wave between them, so we can measure a wavelength for this type of wave as well. Remember that we can define a compression as a point where the matter of the wave is bunched together, for example, here and here. At both of these points, we have coils from either side stopping at their maximum displacement and are about to move back to their equilibrium positions. So we can call these equivalent points, and we can measure the distance between them to find the wavelength. Though it is hard to give an exact location for the compression, so in an exam, you won't need to be super accurate when measuring longitudinal wavelength like this. We can also do the same for rarefactions like these. These are points where the matter is most spread out. Here the coils are about to be brought back together again to form a compression, so we can call them equivalent points and measure the wavelength between them. Notice we have a full cycle of the wave across this distance, with one compression in between. For your exam, make sure you can recall the definition of wavelength and can measure wavelength from images like these.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!